Another stopping criterion, for example, you might say is the same thing, is that you want x of k plus 1 and x of k to be near each other, right? In a sense is that you can say the solution is repeating itself. There is no point in going and continuing the loop anymore, right? So for example, you can say that norm of x of k plus 1 minus norm of x of k is less than some epsilon that you define. Another very popular and very important, which is really widely used, stopping criterion is this maximum number of iteration. Looks simple, right? But you don't want the algorithm run forever. So you usually have the maximum number of iteration like 100, 1,000, right? I don't care if the other two stopping condition are satisfied or not. I want this, when this maximum number of iteration reached, I want to go out of the loop. I have a limited resources, right? So here is the idea. Now, this is important. Here is the idea behind most of these iterative algorithms for nonlinear least square, right? Here is the idea. Once you know this idea, you actually understand these techniques very well. I have looked at a lot of literature, a lot of books. They don't talk about these ideas, right? It's important to know the ideas, why we are doing that. You just have an equation of update, right? It's not about memorization. You need to understand how you get this equation of update and why we are doing this. So look at this idea. It's a two-step process. Step one, you find the affine approximation of your nonlinear equations. You find the affine approximation of your nonlinear equations. Remember, you want to solve a system of nonlinear equation. First, you linearize that. You find the affine approximation, right? Then you use the technique that you have learned in the past to solve the linear least square problem, right? So first you find the affine approximation, and then you use the techniques that you had to solve the least square problem. So that's what you do. Two steps. First, affine approximation to solve the associated least square problem to find the next iterate, right? Okay, good. So that's what I explain here. At each iteration, k, we form the affine approximation f hat of f. So f hat is affine approximation to get them at the current iteration for the x of k, right? So let's see what I mean. So you have this f of hat, x of k. This is the current estimate that we have, right? Is equal to, remember again in that video that I talked about this Jacobian matrix, right? We talked about the linearization. This is just a Taylor approximation. This is nothing but a Taylor, first order Taylor approximation, right? But for a matrix and vector case, when you put it in this format, is equal to f of x of k plus dA of f of x of k times x minus x of k, right? Which this is n by n matrix, Jacobian or derivative matrix, right? So this is the affine approximation of f of x, right, at the point x of k, right, which we want x of k, right, to be near x. More about that later on, right? So I wrote here as well that it's going to be a good approximation if the x and x of k are close together. That's what this says mathematically, that norm of x minus x of k is small, means that x and x of k are close together. So that's the first step. That's the first step, right? If you understand it step by step, right, you will understand it better when we talk about the shortcoming of this algorithm. So first step, find the affine approximation of f. Then to find the xk plus 1, the next estimate, right, of x of k, what we do is find the minimizer of this affine approximation. We find the affine approximation, we minimize it. But this is affine. This is very easy for us to do that. We know how to do it. We spend the entire videos to talk about this stuff, right? What is that equal to? Let's see. This is the equation of the update. But why is that correct? You see these equations everywhere, but why are they correct? So this is the affine approximation. I want to minimize this. I want to minimize this quantity, this norm of this quantity, this one, right? But let's see. What is the x that we want to find? We want to find the next x. Is the variable? This x is the variable. Whatever is multiplied by x is considered A, matrix A, right? So this is our matrix A, right? But we already know this is a matrix A. For a linear case, we proved that d of f of x of k, d of f of x was A, right? We saw that actually here, right? But this is our matrix A because it's multiplied by x. Okay, good. But what is B? Let's just expand this. We have d of f of x of k minus d of f of x of k times x of k plus f of x of k. So this is gonna be what? This is gonna be, when you write it as an equation, ax equal to b, right? When you solve this normal equation, you have ax equal to b, right? So now here, for example, you write it as an equation ax minus b, right? So this is like an ax minus b. So this term is gonna be, what is that? This is d of f times x. Let's have it corrected. This is gonna be like minus b, right? This is ax, this is minus b. So in a sense, what is b for us? Let me see if I can create a new page. It's important to explain this concept. You know what? Let me delete this one. Let me see if I can create a new page here. Okay, now that would be better, right? So in a sense, yes, this one I'm gonna copy these and put them here. Okay, good. So this quantity is nothing but negative b. So b is gonna be d f of x of k minus f of x of k, right? And a is d f of x of k. This is a. Yeah. All right. Very good. So all I want to do is write A transpose, so xk plus 1 is nothing but A transpose A inverse A transpose B. Let's do this one. Is equal to d f of x of k transpose d f of x of k, right? Inverse d f of x of k transpose times this quantity, right? Times this quantity. D f of x, because this is b, x of k minus f of x of k. What I want to do is expand this, but before we expand this, let's just avoid some calculation, right? You see this term here, isn't this the same as that? This is just inverse of that. This term is inverse of this, right? So when you multiply them together, you just get x of k, right? Minus d f of x of k transpose d f of x of k inverse d f of x of k transpose f of x of k. And the minus is coming from this, right? So this is going to be xk plus 1. All right. So this is the equation of update that we derive. It's not anything magical that you see in different books. This is based on this idea. You find the affine approximation, you minimize this affine approximation. It's easy, right? And that's what I said here. I said xk plus 1 is a minimizer of this norm of this affine approximation. Okay, good. Now we know what is d of f of x of k, and we know the update equation, right? This d, since we are using it as a linear least square formulation, this d should have a linearly independent columns like a matrix A, right? So in order for this algorithm to work, the x and x of k should be first close to each other, because otherwise the affine approximation is not making sense. So you are solving a new problem. You're not even solving an original problem, because if your affine approximation is not close to the true function, so you're not even solving the correct optimization problem. That's the first step. That's very important. Second, we want this d to have a linearly independent columns. Okay, good. So what is the algorithm in a nutshell? The algorithm is that you receive a differential function f and initial point x1, your current estimate. It can be anything. And you run this procedure up to k max, which is k max is a maximum number of iteration, like 100, 1,000, right? So form the affine approximation of a function, right, using the current estimate that you have. So for example, using x1 first, then update, find the update, the new update using the least square, and this is the equation of update. All right. So when do we terminate that? Right? You terminate when these two are close, right? So in a sense, you can try this one is less than epsilon. You terminate. Okay, more about that. But before this, I have to address this point. You terminate this when xk plus 1 and xk are close, right? This is termination successfully, right? You terminate successfully. You get a xk plus 1 and this is the better estimate, the best estimate you can find. But what if the D, this matrix df of x of k, the Jacobian derivative matrix, has a linearly dependent column? This is called termination with error. Termination with error. So this is, in a sense, one of the shortcomings of Gauss-Newton technique. We're going to talk about the shortcoming, but this is termination with error. So remember the difference between these two terminations. One of them, the algorithm actually converge. The other one, the algorithm is going to terminate it with error. Okay. Now, another termination condition to understand this better in terms of optimality condition is, I want theoretically, right, this xk plus 1, right, when I converge the solution to be similar to xk, exactly similar to xk, that the solution doesn't change. In a sense, the solution is repeating itself, right? In order for xk plus 1 is equal to xk, I want this quantity to be 0, right? Okay, so I want this quantity to be 0, but at the same time, assume the algorithm is running, is not terminating with error, meaning that the D matrix has a linearly independent columns. Okay, so we proved that before. If the D matrix, we proved that in the past, if this matrix has a linearly independent column, this matrix is considered as a Gram matrix, has linearly independent columns and is a square, therefore it is invertible. So this is fine, right? So if we want this one to be 0, we want this quantity to be 0, right? So that's why I wrote here, if the f of x has a linear independent column, then this one should be equal to 0. But what is this one? This is nothing but the optimality condition when you multiply by 2, and the 2 is not that important. So one of them, a stopping condition you can check is the optimality condition. So add it here as well. We want the norm of d of f of x of k transpose f of x of k to be less than epsilon. You see, actually, in a lot of places, they write this quantity. This is the optimality condition. We want this norm to be 0, but it's very hard to be exactly 0 using the numerical point operation, floating point operation. So we want this norm to be less than epsilon. You can let epsilon to be 10 to the negative 6, 10 to the negative 7, right? Good. So the stopping condition is maximum number of iteration, the norm of these two to be a small. This is a stopping condition with the error, right? And also the optimality condition, of course, which is a very important stopping condition. Okay. Well, what is the shortcoming of that? I already motivated this concept. The algorithm will diverge if x and x of k are not close together. If this norm, the norm of this difference is not small, then these two quantity, right, are not the same. You are not even optimizing it. Your affine approximation is far from the actual function, right? So this approximation, this affine approximation, in a sense, is not a good approximation. So first step is you write the affine approximation, then you minimize this. So what you minimize is something else. It's not even an important thing, right? So that's the first point to consider. The second, what if the column of this matrix are not linearly independent? Then the Gauss-Newton will terminate with error, right? And this is usually the case in practice. The column of this matrix are not linearly independent.